Welcome back. I'd like to start by reviewing what we did last time. We were looking at this function u of t, where u is a vector valued function of a single real variable. And you think of that as being a map from the real line into Rn, and it takes it to some curve. And we have an n by n matrix, and we're interested in the differential equation du dt is equal to a times u. And it's extremely easy to see that the solution to this is u of t is this exponential e to the at times u naught, where u naught is the initial condition, u naught is u of 0. So this is a beautiful solution. It's very easy to remember, but it has the disadvantage that it's hard to compute, because e to the at is hard to compute. Well, the way we compute it is as follows. We write a, let's assume a is diagonalizable with these eigenvectors and eigenvalues. You make this matrix S as usual, and we see that a is S ds inverse, and we see that e to the at is S e to the dt S inverse, and e to the dt is very easy to compute. So we plug that in. U is equal to S e to the dt S inverse u naught. And just as in the difference equations, we're going to replace this S inverse u naught with some fixed vector v naught. I don't care what it is too much. So we'll write it as a random vector c1 through cn. And I get that u of t is equal to S, which is this vector of, matrix of eigenvectors, times e to the dt is this diagonal with the exponentials on the diagonal, times this vector c1 through cn. And I'm going to multiply the second two terms together to get a matrix c1 e to the lambda 1 t down to cn e to the lambda nt. And when you multiply a matrix, the columns of a matrix times a vector like this, what you get is a linear combination of the columns. You get c1 e to the lambda 1t v1 plus cn e to the lambda nt vn. And that's a formula that I gave last time. Okay, I'd like to go on and now talk about stability of these solutions. We've talked about this before, but I'm going to give a somewhat more detailed discussion now. And we're going to have these three different types of stability. So we're looking at this differential equation, and I'm going to give a definition here. The equation or its solutions are stable if the limit of u of t as t goes to infinity is 0 for every starting value u naught. If all solutions go towards 0 asymptotically, they approach 0. It's said to be unstable if, on the other hand, as t goes to infinity, u of t goes to infinity. Well, infinity is not a vector, but you know what I mean. If the length of it gets bigger and bigger, it's getting far away from 0. And that is supposed to happen for some u naught. Not all, but if it happens for any u naught, you say it's unstable. And you say it's neutrally stable, well, if neither of these holds. And how can that be? They don't all go to 0, and none of them go to infinity. Well, how can that be? Let's draw a picture. The stable situation was where all of the curves go towards 0. And what's unstable? Well, unstable, some of them are allowed to go to 0, but at least one has to go to infinity. And the typical picture is like this. They don't all go to infinity. If you start on the x-axis, you go to 0. But since at least one of them goes to infinity, this is unstable. So how can you have not all of them go to 0, but none of them go to infinity? If you think about it, you must have something like this. You're not going to infinity, but you're not going to 0. So you're sort of going around a circle. You're staying in staying a fixed distance or a finite distance away from the origin. And that's a typical neutrally stable solution. So it's really helpful to write down some really fundamental examples, which is to say where the matrix itself is diagonal. And so you can skip the whole diagonalization step and just write everything down directly. And lambda 1 is A, and the eigenvector is 1, 0, and lambda 2 is B with 0, 1. And so the solution looks like C1 e to the at times this plus C2 e to the bt, which is to say C1 e to the at in the first coordinate and C2 e to the bt in the second. And let's just look at what this looks like for different situations, different cases of A and B. The easiest to picture is when A is positive and B is negative. So if you were on the x-axis, that would be C2 is 0 and you'd be going out. And on the y-axis, you're going in. And you need a family of curves which sort of fit with this. And if you think about it, it turns out that these curves, these solutions look like this. They sort of go in towards 0, but then they go out towards infinity. And the y-axis goes to 0, but all others go asymptotically to infinity and close to the x-axis. All right, they're going off to infinity, but they're getting closer and closer to the x-axis. And you can see this if you look at the solution. Since A is bigger than 0, this term is going to infinity. But since B is less than 0, the second term is going to 0. Okay, let's look at the case when A is positive and B is negative. So both axes are pointing out. And how do you put a family of curves that sort of fit nicely here? Well, the key thing to notice is that as t goes to minus infinity, then everything is going to 0. So you must have a bunch of curves that all go through the point 0, and it turns out they look like this. All of the arrows are pointing out, and you're heading out towards infinity like this, sort of in the x direction, but there's a component in the y direction also, and this is unstable. Clearly, every one of those curves is going to 0 to infinity, except of course the 0. So what about the opposite case where A and B are both negative? Well, it's the exact same picture. You just turn all the arrows around. So they're all pointing in towards 0. And as t goes to infinity, all solutions go to 0. Okay, so that's, in some sense, most cases. How do you find a neutrally stable case? Well, there's really a key example of this, which is the following. You take the matrix 0a minus a 0, where a is a positive real number. The eigenvalues of this thing are what? Well, you just check. It's lambda squared plus a squared is equal to 0. So lambda's plus or minus ia, and that's the key point. We have some complex eigenvalues. And the eigenvectors, let's just compute those. When lambda is equal to ia, you get the eigenvector I believe it's I minus 1. And when lambda is equal to minus ia, you get the complex conjugate of that, which is to say minus I minus 1. And you can change the sign to make it I1. So those are our two eigenvectors. So what's the general solution of this equation? U is equal to C1 e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2. And what on earth does this mean? It's got all of these complex numbers in it. I have no idea how to draw a picture of this. Well, of course, the key point is the formula e to the I theta is cosine theta plus I sine theta. And so if we write that out, let's plug that in to the formula, we get this. Okay, let's work this out a little further. By the way, I was missing an I in the formula. Let's write this out. You get C1I cosine minus C1 sine plus C2I cosine plus C2 sine. That's all in the first coordinate. And the second coordinate turns out is similar, of course. I've written it out here. And now we can easily separate the real and imaginary parts of this thing. Just take the terms with or without an I in them. So the real part is, let's see, there's no i's here, so you get C2 minus C1 sine. And on the second coordinate, the terms with no i's are these, which give you C2 minus C1 cosine. And then there's some imaginary stuff, which I am simply going to ignore. So I'm not even going to compute it, just throw it away. And if you look at just the real part, what you get is this constant C2 minus C1, which I don't care what it is, so I'll rename it D. You get D times sine, comma, cosine. That's the real part of this thing. And the length of this vector is D, since sine squared plus cosine squared is equal to 1. And the key point is that since the original matrix was real, it's okay to take the real part of this thing. The real part and the imaginary part separately are going to be solutions. So it was legitimate to throw away the imaginary part. Okay, there are some other special cases which I'm not going to talk about. For example, what if A is equal to B and they're both positive or both negative? Or what if one of them is 0? And so on. I'll skip those for now. And here's the conclusion. So the theorem is we have this differential equation, du is equal to au. And suppose A has eigenvalues lambda 1 through lambda n, which could be real or complex. Then the equation is stable if and only if the real part of all of the lambdas are negative. It's the real part of the lambdas that matter. And it's unstable if at least one of them is positive. The real part of some lambda I is positive. Only one of them needs to be. And how could it be neutrally stable? Well, none of them can be positive. So all of the real part of the lambda i's have to be less than or equal to 0. And if you compare this stable and neutrally stable, well, if they're all less than 0, it's stable. So to be neutrally stable, it must be that one of them is equal to 0. They're all less than or equal to 0, and for at least one of them is equal to 0. So that's the three cases. So let's talk a little bit about the general 2x2 case. Let's compute the determinant of a general thing like this. We've only done this 1,000 times already. You get this formula. And I can't remember whether I've pointed this out before, but the terms in this formula are the trace and the determinant. So the formula is lambda squared minus the trace times lambda plus the determinant. So, well, everything is determined by this formula, so it's all going to be in terms of the trace and the determinant. So let's write it out that way. And let's just solve for lambda in these terms. It's negative b plus or minus the square root of the trace squared minus 4 times the determinant, and all of that over 2. Well, that's interesting. So one of the key things is whether you're going to have real or complex eigenvalues, and that's going to depend whether this thing is positive or negative. So the eigenvalues are going to be real if the trace squared minus 4 times the determinant is greater than or equal to 0, and they're going to be complex if this number is less than 0. So I've abbreviated trace by T and determinant by D. So let's study sort of all 2 by 2 matrices in terms of the trace and the determinant. So what I just said is that T and D determine whether lambda 1 and lambda 2 are real or complex, and that's by computing this quadratic, whether it's positive or negative. Well, stability is also determined by them, clearly. Why is that? Well, we need to check whether lambda 1 and lambda 2 are positive or negative, and how can we tell by looking at the trace and the determinant? Well, of course, when you diagonalize the matrix, it doesn't change the trace or the determinant. So the trace is, as we've said 500 times before, is lambda 1 plus lambda 2, and the determinant is lambda 1 times lambda 2. And you can tell the signs of lambda 1 and lambda 2 by looking at this. For example, if the determinant is negative, at least one of these lambdas has to be negative, one or the other. And one of them has to be positive, and therefore, since one of them is positive, this is unstable, just guaranteed. Determinant less than 0 means it's unstable. If the determinant is greater than 0, how can that happen? Well, they could both be positive or both be negative. And to tell that, you look at the trace. If the trace is positive, it's unstable because they're both positive, and if the trace is negative, then it's stable. So the sign of the determinant and the trace determine stability. So let's look at all matrices parametrized by their trace and the determinant. And let's draw the plane, the trace determinant plane. You're going to plot the trace and determinant of a matrix in this plane. If the determinant is negative, it's unstable. That was the simplest case. If the determinant is positive, well, it's stable or unstable depending on T. So you see this upper right-hand quadrant, they're both positive, so this is the unstable quadrant, and this is the stable quadrant. And how do we tell real and complex? Well, that's given by this T squared, minus 4D, the sign of that. So what's important is this parabola, T squared is equal to 4D, which side of that parabola you're on. So if you're over here to the right where T is very big, then T squared minus 4D is positive. And so this is the real eigenvalue region. And it's T squared which matters, so this is the real region here. And the complex eigenvalues are here above the parabola. So that's kind of a nice picture. It captures all of the possible behaviors of a 2 by 2 matrix depending on the trace and the determinant. And to illustrate how powerful this is, let's do one example. Let's take this 2 by 2 matrix. Its trace is minus 2 and its determinant is 2. So without doing any more work, I can tell exactly what's going on. We're in this region, so that's the stable region, negative trace and positive determinant. And T squared minus 4D is, let's see, it's 4 minus 8 is negative. And that means that we're in the complex eigenvalue region. We're up here. So this must be a stable situation with a complex eigenvalue. And how does that happen? Well, the point is that the solution is going to look like a spiral. like this. And the reason is, let's write out the solution. Well, let's see. We'll compute the eigenvalues from the trace and the determinant. Their sum is minus 2, and the product is 2. And from that, you easily see that they have to be minus 1 plus or minus I. Okay, well, let's see what this looks like. We have these eigenvalues, minus 1 plus or minus I, and the solution is going to be c, some constant, times e to the minus t cosine, e to the minus t sine. So it's just like before, except we have this extra exponential, which I can pull out front. And the point is, before we had a case where the real part was 0, but here, since the real part is minus 1, we're getting this e to the minus t here. And so notice this term here is giving us rotation. We're going around a circle. But this e to the minus t is going to 0. So as you proceed, you dilate, make it smaller, and so you get a spiral pointing in.